What if every star, every swirling galaxy, and every burst of cosmic energy wasn't just random chaos, but part of an ancient, deliberate story? The universe doesn't just exist, it communicates. It writes its epic across the fabric of space and time, in spirals of galaxies that mirror seashells, in the rhythmic flicker of distant quasars like celestial heartbeats, and in the delicate balance of forces that shape everything from atoms to superclusters. This isn't just science, it's the universe whispering its secrets to anyone willing to listen. And today, we're going to decode that cosmic language together. Think about the last time you looked up at the night sky. Those pinpricks of light aren't just scattered randomly, they're part of patterns so vast, so intricate, they've guided civilizations, inspired myths, and even shaped the very structure of mathematics. The golden ratio appears in the curl of a galaxy's arms, just as it does in the petals of a flower. The same laws that govern the orbits of planets also shape the dance of electrons around an atom. It's as if the universe has a signature, a hidden code woven into everything it creates. But why? What's the purpose behind these patterns? Are they accidents of physics, or is there something deeper at play, a story waiting to be read? That's the mystery we're unraveling in this video. We'll journey from the swirling storms of distant nebulae to the mind-bending symmetries of quantum physics, piecing together the clues the cosmos has left for us. You'll discover how black holes might be the punctuation marks in this cosmic narrative, how dark matter could be the invisible ink holding it all together, and why even the chaos of a supernova explosion fits perfectly into the universe's grand design. By the time we're done, you'll never look at the night sky the same way again, because you'll see it for what it truly is. Not just a collection of stars, but a living, breathing story, written in light and time. And you're part of that story too, so let's turn the page together. Every culture that's ever gazed at the night sky has seen more than just stars. They've seen stories, myths, even prophecies written in the constellations. But what if those patterns weren't just imaginative interpretations? What if they were chapters in a cosmic language, written not in words, but in mathematics and physics? Take the golden ratio, a number so precise it appears in the curve of a nautilus shell, the arrangement of sunflower seeds, and astonishingly, the spiral arms of galaxies billions of light years away. Or consider fractal geometry, where the same intricate branching repeats itself in everything from lightning bolts to the vast, glowing tendrils of nebulas. These aren't random accidents, they're signatures of a deeper order, a kind of universal grammar that shapes everything from the smallest particles to the largest structures in existence. Think of it like this: if the universe were a symphony, as physicist Brian Greene suggests, then these patterns are its musical notes, each one obeying the same fundamental laws, whether it's a vibrating string in quantum theory or the gravitational dance of galaxies. Even chaos plays its part. A supernova's explosion might seem like pure destruction, but it scatters the very elements that forge new stars and planets. It's chaos with purpose, disorder that feeds creation, and that's the most fascinating part. This cosmic grammar doesn't just describe the universe, it builds it. The way galaxies cluster along invisible filaments of dark matter, the way black holes spin with eerie precision, it all follows rules we're only beginning to decode. So what does it mean for us? If the universe speaks in patterns, then learning its language could unlock secrets we've barely dreamed of. Maybe dark matter isn't just an invisible scaffold, but a hidden verse in this cosmic poem. Maybe quantum entanglement, the way particles instantly influence each other across vast distances, is a form of celestial dialogue. Every discovery peels back another layer, revealing how deeply interconnected everything truly is. The more we listen, the clearer the message becomes. Chaos and order aren't opposites. They're partners in the universe's endless story. And somewhere in that balance, we might just find the next great revelation. The Fibonacci sequence is nature's quiet masterpiece, a mathematical whisper that echoes from the smallest petals to the grandest galaxies. Picture this: a sunflower's seeds spiral outward in perfect Fibonacci increments, packing the most growth into the tightest space. Now look deeper into the cosmos. The Milky Way's spiral arms unfurl with that same precise ratio, as if the universe sketched them with a divine compass. Why? Because efficiency is the universe's favorite language. Just like a hurricane spiral minimizes turbulence, galaxies twist their stars into Fibonacci-inspired curves to balance gravity's pull with cosmic momentum. It's not just beautiful, it's engineering on a galactic scale. Take Galaxy NGC 5194, the Whirlpool Galaxy. Its arms coil like a nautilus shell, each turn obeying the golden ratio, 1.618, the same number that shapes Renaissance art and ancient pyramids. This isn't coincidence, it's physics optimizing itself. When gravity sculpts a galaxy, the Fibonacci spiral becomes the blueprint for stability, ensuring stars don't collide but glide in harmonious orbits. Even the voids between galaxies cluster in Fibonacci-like hierarchies, as if space itself is counting its steps. But here's the real wonder: this pattern bridges scales. Quantum physicists find Fibonacci sequences in the energy levels of electrons, while astronomers spot them in the clustering of superclusters. It's as if the universe has a favorite rhythm, a pulse that resonates from the infinitesimal to the infinite. So when we trace these spirals across the cosmos, we're not just mapping stars, we're reading the universe's signature. And if nature keeps returning to this sequence, might it hold clues to deeper laws? Could Fibonacci be the universe's way of balancing chaos and order, a secret formula for creation itself? Every spiral we discover is another verse in that cosmic poem, and we're just learning how to listen. Imagine zooming into a single snowflake under a microscope, each delicate branch splitting into smaller, identical branches, repeating endlessly. Now pull back, far back. Those same branching patterns reappear in the veins of a leaf, the forks of a lightning bolt, even the sprawling tendrils of galaxies drifting through the void. This is the magic of fractals, nature's way of crafting infinite complexity from simple, repeating rules. And the universe doesn't just use fractals as decoration, it builds with them. The cosmic web, that vast network of galaxy clusters strung like pearls on invisible threads, isn't random. It's a fractal masterpiece with smaller clusters nesting inside larger ones, all following the same mathematical rhythm. The Crab Nebula tells a similar story. Its swirling gases, ejected from a supernova 1,000 years ago, churn with fractal turbulence, eddies within eddies, each one a miniature echo of the whole. Even the way matter clumps together in space, from the tiniest dust grains to the mightiest superclusters, obeys this scalable logic. It's as if the universe has a favorite recipe, and it keeps reusing it at every scale. Mathematician Benoit Mandelbrot called fractals the geometry of roughness, but they're more than that. They're the universe's most efficient way to pack, organize, and create. A river's branching tributaries minimize energy as they carve the land, just as the cosmic web's filaments guide galaxies along gravity's most economical paths. Here's where it gets stranger. Quantum foam, the seething turbulence of spacetime at the smallest scales, may also dance to a fractal tune. Some theories suggest that if you could peer into the fabric of reality itself, you'd find self-similar patterns frothing in the void, like a cosmic coastline where every new level of zoom reveals another layer of intricacy. Even black holes, those perfect spheres of darkness, might hide fractal secrets in the way their singularities warp the fabric of spacetime. So why does the universe love fractals so much? Think of them as its ultimate time-saving hack. Instead of inventing new rules for every scale, it tweaks the same blueprint. A little more gravity here, a touch less pressure there, and lets infinity handle the rest. The result, a cosmos where order and chaos embrace, where the flutter of a butterfly's wing and the spin of a galaxy are woven from the same mathematical thread. And if we can learn to read that thread, we might just find the universe's signature hidden in plain sight. Symmetry is the universe's silent architect, shaping everything from the subatomic to the cosmic with an almost artistic precision. Picture a star, a near-perfect sphere, its gravity pulling equally in all directions, sculpting it into nature's most balanced form. Now zoom into a snowflake, its hexagonal crystals mirroring the same six-fold symmetry found in the raging storms of Saturn's poles. These aren't accidents, they're clues. The Higgs boson, that elusive particle discovered in 2012, taught us something profound. Symmetry isn't just beautiful, it's the scaffolding of reality itself. When the Higgs field broke symmetry in the early universe, it gifted particles with mass, allowing stars, planets, and eventually us to exist. Without that primordial imbalance, matter would have no weight, no anchor. But here's the twist: symmetry doesn't always mean perfection. Take butterfly wings, their mirrored patterns seem flawless, until you notice the subtle variations, the tiny imperfections that make each one unique. Or supernova remnants, exploding in radiant starbursts of radial symmetry, yet scattering elements unevenly across space. Even the cosmos itself is lopsided. Galaxies cluster more densely in one direction than another, a cosmic tilt we still don't fully understand. This dance of symmetry and asymmetry raises a tantalizing question. Is the universe striving for balance, or is it the imperfections that drive its evolution? Nobel laureate Frank Wilczek likens symmetry to a sculptor's chisel, carving order from chaos. But sometimes it's the cracks in the marble that reveal the true masterpiece. Think of a spinning top, perfectly symmetrical until it wobbles, creating unpredictable, mesmerizing patterns. In quantum physics, particles flicker in and out of existence, their symmetries breaking and reforming like waves crashing on a shore. Even time, which flows forward inexorably, hides broken symmetries in the quantum realm, where particles occasionally defy expectations. So why does nature oscillate between balance and imbalance? Maybe because symmetry is the rule, but asymmetry is the exception that makes things interesting. The universe's lopsided distribution of matter gave birth to galaxies instead of a featureless void. The slight asymmetry in the early cosmos, one extra particle of matter for every billion particles of antimatter, allowed our existence. It's as if the cosmos whispers, perfection is the blueprint, but imperfection is the spark. And in that tension, we find the universe's most creative force, a preference for balance, but a celebration of the flaws that make everything possible. Chaos might seem like the universe's way of thumbing its nose at order, but look closer and you'll find a hidden rhythm beneath the turbulence. Take Jupiter's great red spot, a storm twice the size of Earth that's raged for centuries. From a distance, it's a swirling mess, yet it moves with eerie predictability, trapped between opposing jet streams like a spinning top caught in an invisible groove. This isn't randomness, it's chaos theory in action. Edward Lorenz called it the butterfly effect, the idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas. Now scale that up to cosmic proportions. A tiny gravitational nudge from a passing star, a ripple in space-time from a distant collision. These minuscule shifts can cascade into galactic rearrangements over millennia. Consider the three-body problem, a gravitational puzzle that stumped astronomers for centuries. Three stars orbiting one another should follow neat, predictable paths, except they don't. Their interactions spiral into wild, unpredictable dances, folding space into a labyrinth of possible trajectories. But here's the twist: even in this chaos, patterns emerge. Strange attractors, hidden geometric shapes buried in the math, guide the chaos into repeating loops, like an invisible hand steering the chaos. You can see it in barred spiral galaxies, where stars don't scatter randomly but flow along shimmering arms, pulled by the same forces that make a dripping faucet sometimes fall into rhythmic beats instead of erratic splashes. Entropy, the universe's relentless push toward disorder, seems like chaos's greatest ally. Yet even here there's a catch. When energy pours into a system, like the heat of a newborn star churning a stellar nursery, it doesn't just create chaos. It births structure. Nebulas condense into stars, stars forge heavy elements, and those elements seed new worlds. It's as if the universe uses chaos like a sculptor uses clay, shaping it into something greater. So is the cosmos, a pendulum swinging between order and disorder. Maybe it's something more profound, a place where the two aren't opposites but partners. The same turbulence that fractures a gas cloud also sparks the birth of solar systems. The same unpredictability that scrambles orbits also weaves the Milky Way spirals. Chaos isn't the absence of order, it's the raw material from which order emerges. And in that tension, the universe writes its most compelling chapters, not in perfect symmetry, but in the glorious, unpredictable dance between storm and calm. Down at the quantum level, reality doesn't play by the rules we're used to. Particles exist in a state of constant possibility, flickering between locations, spinning in multiple directions at once, a subatomic ballet where the dancers are everywhere and nowhere until you look. Take the double-slit experiment. Fire a single photon at a barrier with two slits, and instead of choosing one path like a tiny bullet, it behaves like a wave passing through both simultaneously. The result, an interference pattern on the detector screen, a series of light and dark bands that scream one undeniable truth: particles don't just move, they weave. They explore every possible route, and their ghostly overlaps create stark, predictable stripes of order. It's as if the universe whispers, "Here's the script, but lets particles improvise their lines." This isn't just laboratory magic. The same probabilistic rules govern electrons orbiting an atom, photons streaking across the cosmos, even the fleeting existence of virtual particles popping in and out of the void. Richard Feynman's path integral theory paints a mind-bending picture. A particle doesn't take one path from point A to point B. It takes all paths, every conceivable trajectory, and the sum of those possibilities dictates where it lands. Think of it like a cosmic game of telephone, where every version of the message gets sent at once, and only the ones that agree with each other survive. The result, a universe that's messy at the smallest scales but eerily structured when you zoom out. Now here's where it gets cosmic. Those tiny quantum jitters, the minuscule fluctuations in energy fields, might have set the stage for everything we see today. In the first fractions of a second after the Big Bang, quantum ripples could have stretched across the expanding universe, imprinting themselves on the fabric of space-time. Billions of years later, those microscopic wrinkles became the seeds for galaxies, superclusters, and the vast cosmic web. It's a staggering thought. The same uncertainty that makes an electron's position fuzzy might have sculpted the grandest structures in existence. And what about entanglement? When two particles become linked, changing one instantly affects the other, no matter the distance. Einstein called it spooky action at a distance, but it's more like a hidden harmony, a duet sung across light years. Some theories suggest entanglement isn't just a quantum quirk. It could be the glue that holds space-time together, weaving the universe into a single, interconnected tapestry. So is the cosmos just a scaled-up version of quantum weirdness? Maybe not exactly, but the patterns repeat. The same dance of probabilities that guides electrons might echo in the spin of galaxies. The same interference that creates stripes in a lab could mirror the large-scale structure of the universe. From the tiniest particle to the grandest galaxy, the universe seems obsessed with balancing chaos and order, chance and necessity. And if we're brave enough to listen, the quantum realm might just be teaching us the first notes of its symphony. Cosmic microwave background radiation isn't just leftover heat from the Big Bang, it's the universe's baby picture, a frozen moment from when everything was a seething, opaque plasma. Picture this: for nearly 400,000 years after the birth of the cosmos, light couldn't travel freely. Space was a dense, swirling fog of charged particles, trapping photons in a relentless game of cosmic pinball. Then, in a flash, the universe cooled enough for atoms to form, clearing the fog like morning mist burned away by the sun. Those first liberated photons have been traveling ever since, stretched by the expansion of space into faint microwaves that bathe the entire sky. What we're seeing is the universe's first light, a snapshot taken when it was barely a toddler. But here's where it gets fascinating: that afterglow isn't perfectly uniform. Tiny temperature variations, just 1 part in 100,000, paint a speckled pattern across the sky. These minuscule fluctuations are the fingerprints of quantum noise from the universe's earliest moments, magnified by inflation into the seeds of all cosmic structure. Imagine tossing a handful of pebbles into a pond, then watching the ripples expand to ocean-sized waves. Those ripples are the anisotropies we see in the CMB, the gravitational blueprint for everything that came after. Without those microscopic irregularities, matter would have spread evenly, leaving no clumps to collapse into galaxies, stars, or planets. We owe our existence to those faint whispers of imbalance. The Planck satellite's map of the CMB reads like a cosmic treasure hunt. Its rainbow-colored splotches align almost perfectly with predictions from inflationary theory, except for a few stubborn anomalies. Take the so-called axis of evil, a mysterious alignment of temperature fluctuations that defies conventional models. Some researchers suggest it hints at a pre-Big Bang structure, a shadow of something older lurking beyond our observable horizon. Others propose it's evidence of a multiverse, where our universe brushes against others in ways we can't yet comprehend. Then there's the cold spot, an unusually chill region that might be a bruise from a collision with another universe during inflation. These oddities aren't flaws in the data, they're clues, tantalizing hints that the CMB might hold chapters of cosmic history we haven't even imagined. What makes the CMB so extraordinary isn't just what it confirms, but what it questions. It's a Rosetta Stone written in the language of thermodynamics, quantum mechanics, and gravity, a text we're still learning to decipher. Every new observation peels back another layer, revealing how much we still don't understand about the universe's first moments. The patterns in that ancient light aren't just echoes of the past, they're signposts pointing toward mysteries we've yet to unravel. And somewhere in those subtle variations, the cosmos might be hiding its next great revelation. Dark matter doesn't just lurk in the shadows, it builds them. Imagine an invisible hand molding the cosmos, shaping galaxies into delicate filaments that stretch across billions of light years like threads in a spider's web. This isn't science fiction, it's the chilling precision of dark matter's gravitational grip. The Millennium Simulation, a supercomputer's attempt to map the universe's growth, reveals something astonishing. When you let dark matter's pull dictate the rules, virtual galaxies arrange themselves into structures eerily similar to the real cosmic web. Without dark matter's scaffolding, the universe would look like a sparse, formless void. Instead, we see clusters stacked like beads on a string, galaxies huddled along shimmering tendrils of gravity, a design so intricate it couldn't be random. But here's the puzzle: dark matter refuses to show its face. We know it's there because we see its gravitational signature, the way galaxies spin faster than they should, the way light bends around empty space as if something massive lurks unseen. Yet despite decades of hunting, we've never directly detected a single particle of it. Is it because dark matter doesn't interact with light or matter the way ordinary particles do? Or could it be something even stranger, like sterile neutrinos, ghostly particles that barely acknowledge the rest of reality? Some theorists propose actions, hypothetical particles so lightweight they could drift through planets like fog through a screen door. The bullet cluster offers a rare glimpse into dark matter's behavior. When two galaxy clusters collided, their visible gas slammed together, heating up and slowing down, but their dark matter kept right on going, sliding past the wreckage like a phantom train. This separation proved dark matter isn't just an illusion, it's a physical substance with its own rules. Yet even here, mysteries multiply. Why doesn't it clump as densely as simulations predict? Why do some dwarf galaxies seem to lack the dark matter halos we'd expect? Perhaps dark matter isn't one thing but many, a hidden ecosystem of particles, each playing a different role in the cosmic story. Or maybe we're missing a fundamental piece of gravity's puzzle, a twist in the laws we thought we knew. Every unanswered question is a breadcrumb leading us deeper into the universe's grand design. And until we solve it, we're like readers straining to decipher a manuscript where half the ink is invisible, knowing the story is there, but missing the words that make it whole. Dark energy isn't just a scientific mystery, it's the universe's greatest plot twist. Picture this: every galaxy, every star, every speck of dust is being pushed apart by an invisible force that grows stronger as space expands. It's as if the cosmos is writing its own sequel, and dark energy is the unseen hand turning up the speed. When astronomers first discovered this acceleration in the late 1990s, it shattered expectations. Gravity was supposed to slow the universe's expansion, not rev it like a cosmic engine. Yet here we are, watching galaxies flee from one another faster with each passing moment, as if the fabric of reality itself has a secret agenda. The simplest explanation is Einstein's cosmological constant, a fixed energy woven into empty space. But what if dark energy isn't constant at all? Enter quintessence, a theoretical field that ebbs and flows over time, its push growing stronger or weaker like the tides of an unseen ocean. Some models suggest it could eventually tear atoms apart in a catastrophic big rip, while others hint it might fade, leaving the universe to expand forever into a cold, silent darkness. The stakes couldn't be higher. Dark energy doesn't just shape the universe's fate, it rewrites it. Then there's the Hubble tension, a nagging mismatch in how fast we think the universe is expanding. Measurements from nearby supernova clash with predictions based on the cosmic microwave background, as if the cosmos can't decide on its own pace. Is this a clue that dark energy evolves, or evidence of entirely new physics? The Nancy Grace Roman Space Telescope, set to launch in the next few years, might hold answers. By mapping millions of galaxies, it could reveal whether dark energy's push has changed over cosmic history, a plot twist even our best theories haven't anticipated. Here's the wildest part: dark energy might not be a thing at all. Some theorists propose it's an illusion, a side effect of our incomplete understanding of gravity on cosmic scales. Others wonder if we're seeing shadows of extra dimensions or echoes of a multiverse pressing against our own. Every hypothesis feels like a new page in a thriller, each with its own cliffhanger. One thing's certain, dark energy is the ultimate wildcard. It could be the universe's way of keeping us curious, ensuring the story never ends neatly. And as long as galaxies keep racing into the void, we'll keep chasing the mystery, one observation at a time. Black holes aren't cosmic dead ends, they're more like exclamation points in the universe's ongoing narrative. Picture the accretion disk of a supermassive black hole like M87 star, a swirling maelstrom of gas and dust glowing white-hot as it spirals inward. But hidden in that chaos is a rhythm, X-ray quasi-periodic oscillations or QPO, pulsing like a cosmic metronome. These aren't random flickers, they're clues to the black hole's spin, its mass, even the way space-time itself twists just outside the event horizon. It's as if black holes broadcast their secrets in a code we're only beginning to crack. Then there's the photon ring, that eerie, near-perfect halo captured by the Event Horizon telescope. Light doesn't just bend around a black hole. It gets trapped in orbit, circling like a car on a cosmic racetrack before either plunging into darkness or escaping to our telescopes. This isn't just a pretty picture. It's a direct snapshot of Einstein's general relativity in action, proving space-time isn't just a stage but an active participant in the drama. But black holes don't just sit quietly. When two collide, they send ripples through the fabric of reality itself, gravitational waves that chirp upward in pitch as they spiral toward catastrophe. LIGO detections of these mergers have given us a whole new way to hear the universe, turning space-time into a vast musical instrument. And somehow, even in their final moments, these chaotic collisions produce signatures so clean, so predictable, they've become standard candles for measuring cosmic distances. Yet the most mind-bending twist might be Hawking radiation, the faint glow of particles born from quantum fluctuations at the edge of a black hole's grasp. Over eons, this slow leak could cause even the mightiest black hole to evaporate, turning what we thought was a one-way trap into a transient phenomenon. It's a reminder that nothing in the universe is truly permanent, not even the darkest voids. So are black holes destroyers or creators, both. The same forces that shred stars also seed galaxies with heavy elements forged in their violent outskirts. The same gravity that crushes matter into oblivion might also power quasars, the brightest beacons in the cosmos. They're the ultimate paradox, cosmic wrecking balls that somehow sculpt the universe's grandest structures. And in that tension, they reveal something profound, that destruction and creation aren't opposites, but two sides of the same cosmic coin. Neutron stars are nature's ultimate pressure cookers. Stellar corpses so dense, a single teaspoon of their material would weigh as much as a mountain. When a massive star collapses in a supernova, its core doesn't just shrink. It's crushed into a city-sized sphere where atoms surrender, merging their protons and electrons into a sea of pure neutrons. The result, an object with the mass of the Sun packed into a space no wider than Manhattan, spinning faster than a blender on its highest setting. Some of these remnants, called pulsars, become cosmic lighthouses, firing beams of radiation from their magnetic poles with such precision, they rival the best atomic clocks on Earth. The Crab pulsar, born in a supernova observed in 1054, still spins 30 times per second, its rhythmic flashes visible even through amateur telescopes. But neutron stars aren't just accurate, they're audacious. Take the Hulse-Taylor binary pulsar, two neutron stars locked in a gravitational tango. As they spiral closer, they lose energy in the form of gravitational waves, exactly as Einstein predicted. This cosmic waltz earned its discoverers a Nobel Prize and gave us the first indirect proof of ripples in spacetime. Yet for all their precision, some neutron stars break the mold entirely. Magnetars, for instance, wield magnetic fields a quadrillion times stronger than Earth's. When their crusts crack under unimaginable strain, they unleash starquakes, violent tremors that ripple through the star's crystalline surface, releasing flares of gamma rays so intense they've temporarily blinded satellites halfway across the galaxy. What's truly mind-bending is what's happening beneath the surface. A neutron star's crust isn't just dense, it's structured like a cosmic lasagna, with layers of neutron-rich material dubbed nuclear pasta. Some sections form long, spaghetti-like strands, others flatten into sheets like lasagna, all under pressures so extreme they defy the laws of chemistry as we know them. These bizarre structures might even vibrate like tuning forks, sending ripples through spacetime itself, gravitational waves we could one day detect. Could neutron stars hold the key to quantum gravity? Their cores may harbor exotic states of matter, quark, gluon plasma, or even free-floating strange quarks, offering a glimpse into physics beyond the standard model. Every pulse, every flare, every quake is a message in a bottle drifting across the cosmic ocean. And if we learn to read them, we might just crack the universe's deepest codes. Exoplanets aren't just dots on a star chart, they're a cosmic carnival of extremes, each one defying expectations in its own way. Take WASP-12b, a gas giant so close to its star, its atmosphere is boiling away into space, leaving a ghostly tail of vaporized metal. Or Kepler-10b, a scorched world with lava oceans so vast they could swallow continents whole. Then there's 55 Cancri e, a planet twice Earth's size where carbon pressures might have crushed its core into a glittering diamond the size of a star. These aren't just oddballs, they're proof that the universe has a flair for the dramatic, crafting worlds wilder than any sci-fi writer could dream up. But the real magic lies in how these planets move. Around the star TRAPPIST-1, 7 Earth-sized worlds orbit in near-perfect resonance, their years ticking like gears in a celestial clock. For every 2 orbits the innermost planet completes, the next one finishes 3, the next 4, and so on, a gravitational ballet so precise. It's as if the system was tuned by a master composer. This harmony isn't rare either. Over half of multi-planet systems show similar resonant chains, suggesting that planets often form in sync, then lock into these rhythmic patterns over eons. It's a cosmic phenomenon that turns entire star systems into music boxes, their orbits humming with mathematical beauty, yet for every rule there's a rebel. Some exoplanets, like HD 106906b, orbit backward, defying their star's spin in a gravitational mutiny. Others, like rogue planet PSOJ 318.5-22, drift alone through the void, untethered to any star at all. Even our own solar system might once have harbored a 5th giant planet, ejected in a long-forgotten gravitational showdown. These outliers aren't glitches, they're reminders that chaos and chance still sculpt the cosmos, no matter how orderly the patterns seem. The hunt for these worlds has rewritten astronomy's playbook. The Kepler Space Telescope didn't just find planets, it revealed that stars often host more worlds than our own sun does, with some systems packing half a dozen planets into orbits smaller than Mercury's. Its transit method, watching for the telltale dimming of starlight as planets pass by uncovered thousands, proving that planets aren't the exception but the rule. And with next-gen telescopes like JWST analyzing exoplanet atmospheres, we're not just mapping these worlds anymore, we're sniffing their air, searching for the chemical whispers of water, methane, or even signs of life. So what does it all mean? Maybe exoplanets are nature's way of showing off. proving that the universe has more tricks up its sleeve than we ever imagined. Or maybe they're cosmic breadcrumbs, leading us toward an even bigger revelation that the story of planets, from the fiery to the frozen, is just one chapter in a grander tale. Either way, every new discovery peels back another layer, revealing just how little we truly know about the worlds beyond our own. Galaxies aren't solitary islands in the void, they're predators and prey locked in an endless cosmic dance. Look at the Milky Way, our own galactic home, and you'll find its halo littered with the remains of past meals, streams of stars like celestial breadcrumbs, tracing the orbits of dwarf galaxies it consumed billions of years ago. These ghost streams are more than just relics. They're evidence of a universe where growth often comes through collision. Take the Sagittarius dwarf spheroidal galaxy, currently being torn apart by our galaxy's gravity, its stars strewn across the sky in a shimmering arc. This isn't destruction, it's transformation. The Milky Way isn't just swallowing its neighbor, it's absorbing its raw materials, recycling them into new stars, new possibilities. But the real spectacle lies ahead. In roughly 4 billion years, the Milky Way and Andromeda will slam into each other in a slow-motion crash that will rewrite both galaxies forever. Simulations show their spiral arms unraveling like tangled thread, their cores merging into a single, blazing ellipsoid, a new galaxy nicknamed Milkdromeda. The process won't be violent in the way we imagine. Stars are so far apart that few will collide. Instead, gravity will sculpt them into new orbits, triggering bursts of star formation in some regions while quenching it in others. It's like watching two crowds merge. Individuals don't crash, but the collective motion creates something entirely new. The Tadpole Galaxy offers a preview of this chaos. Its long, star-studded tail isn't just decoration, it's the aftermath of a smaller galaxy being ripped apart, its stars flung into space like paint splattered across a canvas. Yet even in this violence, there's beauty. The same gravitational forces that tear galaxies apart also compress gas clouds, igniting starbursts so intense they outshine entire galaxies. The Antennae galaxies, a pair mid-collision, blaze with newborn stars, their spiral arms twisted into glowing bridges of dust and light. So is galactic cannibalism cruel or creative? Both. Without these mergers, galaxies would starve, cut off from the fresh gas and stars they need to grow. Yet each collision also erases something old to make way for the new. It's a cycle as old as the universe itself, a reminder that even in the cosmos there's no creation without destruction, and somewhere in that balance the universe keeps writing its next chapter. Supernova aren't just explosions, they're the universe's greatest alchemists, transforming the simplest elements into the stuff of planets, jewelry, and even life itself. Picture a dying star, its core collapsing under its own weight in a fraction of a second. The shockwave rips outward, blasting the star's outer layers into space at millions of kilometers per hour, a fireball so bright it can outshine an entire galaxy. In that cataclysm, something miraculous happens. The intense heat and pressure forge elements heavier than iron, from cobalt to uranium, scattering them like cosmic confetti across the void. Every gold ring, every uranium fuel rod, even the calcium in your bones, they all trace back to these stellar detonations. But not all supernovae play by the same rules. Type Ia supernova, the universe's standard candles, burn with such consistent brightness, astronomers use them to measure cosmic distances. Their predictability led to the jaw-dropping discovery of dark energy, the force accelerating the universe's expansion. Yet even these reliable markers have their rebels. SN 2006 GZ, for instance, defied expectations by shining brighter and longer than any model predicted, hinting at exotic physics or unusual stellar compositions we've yet to unravel. It's as if the cosmos keeps a few wild cards up its sleeve, reminding us that for every rule, there's an exception waiting to rewrite the textbooks. Then there's the drama of neutron star mergers, collisions so violent they ripple spacetime itself. When LIGO detected the first gravitational waves from one of these events in 2017, telescopes swiveled to catch the aftermath, a kilonova, a glowing cloud of neutron-rich debris where gold and platinum coalesced by the ton. A single merger can forge hundreds of Earth masses worth of precious metals, flinging them into the cosmos to one day seed new worlds. Suddenly, the phrase stardust takes on a whole new meaning. Your wedding band might literally be shattered star stuff, forged in a cataclysm older than the solar system. So why does the universe bother with such spectacular violence? Because without it, complexity couldn't exist. The first stars burned pure hydrogen and helium, their deaths seeding space with carbon, oxygen, and nitrogen, the ingredients for water, air, and DNA. Later generations of stars, enriched by these ashes, cooked up even heavier elements. It's a cycle as old as time. Stars die so that new stars, planets, and life can rise from their wreckage. The Crab Nebula, the glowing remnant of a supernova witnessed in 1054, isn't just a tomb, it's a nursery. It's swirling gases already condensing into the next generation of stellar embryos. And here's the kicker, we're part of that story too. The iron in your blood, the iodine in your thyroid, the phosphorus in your DNA, they all came from stars that died billions of years ago. Supernova aren't just cosmic fireworks, they're the universe's way of recycling itself, turning destruction into the raw materials for creation. So the next time you look up at the night sky, remember, you're not just observing the stars. You're made of them. Quasars blaze across the cosmos like ancient lighthouses, their light piercing through billions of years of cosmic history. These celestial powerhouses are supermassive black holes, some weighing billions of times the mass of our sun, gorging on gas and dust with such ferocity that their accretion disks glow brighter than entire galaxies. But what makes them truly extraordinary isn't just their brilliance, it's what they reveal about the universe's wild teenage years. Take Euler's J1342 plus 0928, a quasar so distant its light left when the cosmos was just 690 million years old. Its existence defies expectations. How could a black hole grow so massive so quickly when the universe itself was barely out of infancy? The answer might lie in the chaotic dawn of time. In the early universe, vast reservoirs of cold gas collapsed directly into black holes without forming stars first, a shortcut to cosmic gigantism. These primordial monsters gorged themselves in an era when galaxies were little more than swirling clouds of raw material. Their intense radiation, pouring out like a cosmic blowtorch, helped reionize the universe, tearing apart the fog of neutral hydrogen that once filled space and making the cosmos transparent to light for the first time. Without quasars, the universe might still be shrouded in a featureless gloom. Yet quasars aren't just relics, they're storytellers. Their spectra, stretched and redshifted by the expansion of space, carry chemical fingerprints of the gas they've devoured. The Sloan Digital Sky Survey has mapped hundreds of thousands of them, revealing how they cluster along filaments of dark matter like pearls on an invisible string. This cosmic web, traced in quasar light, shows us the scaffolding upon which galaxies are built. Even more astonishing, some quasars exhibit broad absorption lines, telltale signs of gas being blasted outward at nearly a fifth the speed of light, proof of the unimaginable forces at work around these gravitational maelstroms. But the real surprise, quasars flicker. Their brightness can change dramatically over days or even hours. a clue that the frenzied feeding happening near their event horizons unfolds on scales smaller than our solar system. It's like watching a storm rage inside a teacup, a testament to the extreme physics governing black holes. And when two quasars are found side by side, it's often a sign of colliding galaxies, their central black holes destined to spiral together in a gravitational wave generating dance billions of years from now. What's mesmerizing is how these beacons of the early universe still shape the cosmos today. The same processes that powered quasars, gas spiraling into black holes, continue in quieter form in galaxies like our own Milky Way, just at a gentler pace. Even Sagittarius, a star, the dormant giant at our galaxy's heart, might have been a quasar once, its glory days lost to time. So when we study quasars, we're not just peering into the past, we're uncovering the hidden rhythms that govern all galaxies, including our own. Their light is more than a beacon. It's a time machine illuminating the universe's most turbulent era and showing us how the chaos of youth forged the cosmos we know today. Cosmic inflation is the universe's greatest magic trick, an expansion so rapid it makes the Big Bang look slow motion. Picture this, in less than a trillionth of a second, space itself stretched from smaller than an atom to nearly the size of a grapefruit. That's like inflating a single grain of sand to the scale of the observable cosmos in the time it takes light to cross a single proton. This wasn't just fast, it was exponential, a runaway explosion of spacetime that ironed out wrinkles in the early universe like steam smoothing a crumpled sheet. Without inflation, the cosmos might have been a chaotic mess of tangled gravity and uneven temperatures. Instead, it gave us a universe astonishingly uniform, yet subtly textured with the seeds of galaxies. But how do we know this happened? The clues are written in the cosmic microwave background, that faint afterglow of the Big Bang. Tiny temperature variations, those 1 part in 100,000 fluctuations, match inflation's predictions with eerie precision. Even more tantalizing are the primordial gravitational waves inflation should have generated, ripples in spacetime itself. Projects like BICEP and Keck scan the CMB for their faint imprint, a curling polarization pattern nicknamed B modes. Finding them would be like discovering the fingerprints of the universe's first moment. Yet so far, the signal remains elusive, hidden beneath interstellar dust or perhaps quieter than theorists expected. The real controversy lies in what triggered inflation and how it ended. Some models suggest it was a one-time quantum fluctuation, a bubble of false vacuum energy that decayed into the universe we know. Others propose eternal inflation, where our cosmos is just one bubble in an endless froth of universes, each with its own laws of physics. Imagine a cosmic foam with every bubble a separate reality, some barren, some brimming with life, most utterly alien. It's a dizzying thought, but not without evidence. If inflation is eternal, the patterns in the CMB might hold statistical anomalies, subtle asymmetries betraying collisions with other universes in the distant past. Then there's the cyclical model, where inflation isn't the beginning but a recurring phase. Picture two universes colliding in a higher dimensional space, their impact igniting a new inflationary epoch like a cosmic reset button. This isn't science fiction, it's string theory's ekpyrotic scenario, where the Big Bang was just the latest chapter in an infinite saga of cosmic rebirth. The math works, but the proof remains as elusive as the multiverse itself. What makes inflation so compelling isn't just its explanatory power, it's its audacity. A process lasting a fraction of a second set the stage for everything: the distribution of galaxies, the arrow of time, even the very laws of physics. And if we're ever able to peer beyond it, we might finally answer the ultimate question: was our universe inevitable, or just one roll of the dice in a game without end. The idea of a multiverse isn't just science fiction, it's a serious scientific hypothesis that redefines what everything could mean. Picture an endless cosmic library where each book tells a different version of reality, with tweaked physics, alternate histories, even entirely new dimensions. String theory, our best stab at unifying gravity and quantum mechanics, suggests this might not be fantasy. It proposes a landscape of possible universes, 10 to the power of 500 of them, each with its own unique constants and laws. In some, gravity might be stronger, snuffing out star formation before life could begin. In others, electromagnetism could be weaker, preventing atoms from ever bonding. We just happen to live in one where the numbers lined up perfectly for galaxies, planets, and us. But how would we ever know the cosmic microwave background, that ancient light from the universe's infancy, holds tantalizing clues? Some researchers argue that unusual cold spots or strange asymmetries in its patterns could be bruises, places where our bubble universe bumped against another in the violent turbulence of cosmic inflation. It's like finding a fingerprint on a window, hinting at something just beyond the glass. The Planck satellite's data has fueled these speculations, though skeptics counter that dust or statistical flukes could explain the anomalies. For now, the evidence remains elusive, like whispers in a thunderstorm. Physicist Max Tegmark organizes the multiverse into 4 levels, each wilder than the last. The first is simple, an infinite cosmos where every possible arrangement of matter repeats eventually, meaning somewhere out there, another you is reading this script on an identical Earth. The second level introduces other bubble universes, each with different physical constants, born from eternal inflation's endless froth. Level 3. The many worlds interpretation of quantum mechanics, where every decision branches reality into new timelines. And the fourth, the most abstract, suggests that all mathematically possible structures exist somewhere, making universes as inevitable as numbers. Critics argue this veers into philosophy, not physics. Without observable proof, how can a theory be scientific? Yet supporters counter that the multiverse isn't just a guess, it's a prediction. Inflationary cosmology and string theory naturally lead there, much like relativity predicted black holes long before we saw one. And if we ever detect those telltale gravitational waves or anomalies in the CMB, the debate could shift overnight. What's fascinating isn't just the science, it's the storytelling. If we're one thread in an infinite tapestry, does that make our existence insignificant or astonishingly rare? Maybe both. The multiverse doesn't diminish our universe's story. It frames it as one of countless variations, each a unique experiment in the grand laboratory of reality. And whether it's proven or not, the idea alone stretches our imagination further than the cosmos itself, challenging us to rethink what everything really means. Time's arrow doesn't just tick forward, it carves the universe's story into existence. Think of an egg shattering on the floor. You never see the mess leap back into the shell because entropy, the measure of disorder, always climbs. The second law of thermodynamics isn't just a rule, it's the reason we remember the past but not the future. Yet here's the cosmic mystery. If disorder always increases, why was the Big Bang so astonishingly ordered? The early universe was a near-perfect soup of particles, a state of improbably low entropy. It's like finding a library where every book starts alphabetized, only to slowly scatter into chaos. This is the heart of the past hypothesis, the idea that our universe began in a bizarrely specific configuration, setting time's arrow in motion. Some theorists argue this low entropy starting point wasn't accidental but necessary, a cosmic quirk that allowed complexity to emerge. Without it, stars wouldn't burn, life wouldn't evolve, and stories like ours would never be told. But what chose this initial order? One provocative answer lies in black holes. These gravitational monsters are entropy factories, their event horizons hiding more disorder than any other object in the cosmos. When matter falls in, it's not destroyed, it's scrambled into quantum bits, maximizing entropy in a way that bends the rules of information itself. Yet black holes also deepen the puzzle. The information paradox asks how data about swallowed particles can vanish inside a black hole, yet somehow persist in the universe's ledger. If entropy is about counting possibilities, how does the cosmos keep track? This tension hints at something profound. Time's flow might not be fundamental but emergent, a side effect of deeper quantum processes. Loop quantum gravity, for instance, suggests spacetime is woven from tiny, entangled threads, a fabric where time arises from their interactions, not the other way around. Meanwhile, the universe's expansion adds another layer. As space stretches, it cools, creating pockets where entropy can locally decrease like eddies in a flowing river. Stars form, life emerges, and for a fleeting moment, order triumphs. But this is borrowed time. Eventually, expansion will dilute everything into a cold, uniform haze, a state called heat death, where entropy maxes out and time loses all meaning. So is time's arrow written into the cosmos, or is it a temporary illusion? The answer might lie in the quantum realm, where particles flirt with time's symmetry, or in the cosmic microwave background's faint whispers. Either way, time isn't just a backdrop, it's the spine of reality's story, the invisible hand guiding every collision, every birth, every thought. And somewhere in its relentless push forward, the universe finds a way to turn chaos into meaning. What if the universe isn't just telling a story, but aware it's being read? The idea sounds like philosophy, but it emerges from quantum labs where particles change behavior the moment we measure them. In the double-slit experiment, electrons act as waves when unobserved, painting an interference pattern on the detector. But the instant a scientist peers at which slit they pass through, they snap into crisp particle form, as if playing to an audience. Physicist John Wheeler took this further, proposing reality requires observers to crystallize it like a cosmic game of 20 questions where the answers only exist when someone asks. His participatory universe suggests we're not just passive witnesses but essential collaborators, conjuring reality into being by the act of perception. This isn't just quantum quirkiness, it echoes in the eerie fine-tuning of the cosmos. The anthropic principle notes how dozens of physical constants, gravity's strength, the mass of electrons, are dialed to impossible precision for life to exist. Nudge anyone and stars wouldn't ignite, atoms wouldn't bond, and complexity would crumple. Some argue this hints at a multiverse, where infinite universes with random constants exist, and we simply inhabit the lucky one. But others wonder, what if the fine-tuning reflects a deeper reciprocity, like a cosmic version of the observer effect, where the universe's laws stabilize because consciousness emerges to witness them? The implications spiral into metaphysics. If observation shapes reality, could the first life forms gazing at the stars have helped fix the laws of physics? Ancient Hindu texts describe the universe as a dream of Brahman, while modern quantum physicists speak of quantum decoherence, the idea that observation collapses probabilities into concrete outcomes. Even black holes, those perfect entropy machines, might encode information on their event horizons like cosmic hard drives, preserving a record of what fell in. It's as if the universe insists on being seen, its story only complete when acknowledged. Yet skeptics push back. Maybe consciousness isn't special, just another emergent property of complex systems, like hurricanes or neural networks. The universe got lucky with its constants, and here we are. But the debate itself reshapes the narrative. Whether we're readers, scribes, or accidental characters, our quest to understand the cosmos might be the universe's way of understanding itself. And in that loop of observation and creation, the line between science and story blurs into something far stranger, a tale where the teller and the told are one. The Gaia Hypothesis turns our planet from a passive stage into a living character in the cosmic story. Imagine Earth not just as a rock floating in space, but as a vast, self-regulating system where oceans, atmosphere, and life itself work in concert like organs in a body. When volcanoes spew carbon dioxide, plants thrive and absorb it. When temperatures rise, more clouds form to reflect sunlight. These aren't coincidences, they're feedback loops so precise they've kept Earth habitable for billions of years despite solar flares, ice ages, and asteroid strikes. It's as if the planet has a kind of metabolism, constantly adjusting its rhythms to maintain equilibrium. But here's the mind-bending question: if Earth can do this, might other worlds? Astronomers scanning exoplanet atmospheres for biosignatures, gases like oxygen or methane that hint at life, might actually be detecting planetary-scale Gaian systems at work. Take K218b, a super-Earth with water vapor and possible oceans in its sky. Could its atmosphere be actively managed by unseen organisms, just as microbes helped shape ours? Or consider Venus, Earth's twisted twin. Its runaway greenhouse effect shows what happens when feedback loops spiral out of control. The difference between a living world and a dead one might come down to whether it can heal its own climate. Life itself seems obsessed with tipping the scales. Extremophiles organisms thriving in boiling vents or Antarctic ice prove biology can adapt to almost any niche. But what if life doesn't just adapt to environments? What if it engineers them? Cyanobacteria oxygenated Earth's atmosphere 2 billion years ago, making complex life possible. Now humans' unwitting Gaian agents are altering the carbon cycle with fossil fuels. Our very presence raises a profound possibility. Maybe life isn't just a passenger on planets. Maybe it's the pilot. This shifts how we search for cosmic company. Instead of just hunting for water or oxygen, we might look for planets whose chemistry seems suspiciously stable, a sign something's maintaining the balance. Technosignatures, like industrial pollutants in alien atmospheres, could reveal civilizations playing the Gaian game. Or we might find worlds frozen in perfect harmony, their biospheres locked in cycles we can barely comprehend. Either way, the universe's story grows richer. Life isn't just a rare accident, it could be a fundamental force, as woven into cosmic evolution as gravity or light. And if that's true, every living world might be telling its own version of the same epic, a tale of chaos and balance, written not in starlight but in the breath of planets. The universe sprawls across 93 billion light-years, sprinkled with 2 trillion galaxies and countless planets in the habitable zone. So where are all the aliens? This is the Fermi Paradox, the haunting silence that greets our search for cosmic neighbors. Enrico Fermi first posed the question over lunch in 1950, calculating that even at modest speeds, a civilization could colonize the galaxy in a few million years, a blink in cosmic time. Yet our radio telescopes hear only static. The solutions to this paradox range from chilling to hopeful, each a different chapter in the universe's untold story. Take the Great Filter Theory, a hypothetical barrier that prevents life from advancing to interstellar scales. Maybe it's behind us. The leap from simple cells to complex life could be astronomically rare, making Earth a fluke. Or worse, it's ahead. Nuclear war, runaway AI, or some unseen catastrophe could doom all advanced civilizations before they spread. The eerie emptiness of our galaxy might be a graveyard of dead pioneers, their ruins lost to time. Others propose kinder answers. The zoo hypothesis suggests advanced species observe us like wildlife, withholding contact until we're ready. Or perhaps they've transcended physical forms, uploading into digital realms or dark matter networks invisible to our instruments. There's even the galactic internet idea, that civilizations communicate via neutrino pulses or quantum entanglement, leaving our radio searches as archaic as smoke signals. Projects like Breakthrough scan millions of stars for technosignatures, narrowband radio signals, laser pulses, even Dyson spheres harvesting starlight. So far, nothing, but absence of evidence isn't evidence of absence. The universe is vast, and we've barely scratched the surface. A civilization just a few centuries ahead of us might use technologies we can't yet fathom. Imagine ants trying to detect Wi-Fi. The signals are there, but the ants lack the tools to see them. Then there's the darkest possibility: we're first. If life needs rare cosmic conditions, a stable galactic neighborhood, precise elemental abundances, we might be the universe's opening act, the first sparks in a fire yet to spread. Or maybe life is common, but intelligence isn't. Dolphins and octopuses are brilliant, yet neither builds radios. Intelligence could be an evolutionary accident, not an inevitability. The paradox forces us to confront our place in the story. Are we a lonely accident, or one voice in a chorus we can't yet hear? The answer might rewrite not just science but philosophy. Until then, the silence isn't empty, it's a question hanging in the dark, waiting for a reply. The Kardashev scale isn't just a ranking of civilizations, it's a roadmap of cosmic potential, sketching how intelligence might climb from planetary toddlers to galactic architects. Picture a Type 2 civilization, masters of stellar energy, constructing Dyson swarms, vast arrays of orbiting solar collectors that encase their star like a shimmering net, capturing every photon. This isn't sci-fi, it's physics. Freeman Dyson himself proposed that such megastructures would radiate waste heat detectable across light years. Astronomers have already scanned thousands of stars for infrared signatures that don't match natural models, hunting for these cosmic fingerprints of ambition. But why stop at one star? A Type 3 civilization would command the energy output of an entire galaxy, weaving black holes into power plants or harvesting pulsar beams. Their engineering might reshape the Milky Way's structure, leaving patterns visible in the distribution of stars or the flicker of quasars. Some theorists suggest fast radio bursts, those mysterious milliseconds-long blasts from deep space, could be evidence of interstellar power grids or propulsion systems operating at scales we can barely fathom. The absence of obvious Type 3s raises a haunting question. Is the universe too young for such giants, or are we just not recognizing their works? Consider the timeline. The cosmos is 13.8 billion years old, a blink compared to the trillions ahead. Earth civilization is a newborn in this story, barely scratching Type 1 status, where we harness all our planet's energy. Maybe advanced cultures are still rare, scattered like islands in an ocean of time. Or perhaps they've transcended physical forms, uploading into quantum clouds or dark matter networks, leaving no trace we can detect. The scale doesn't just measure energy, it hints at evolution's arc. A Type 4 might manipulate the fabric of spacetime itself, turning singularities into tools or rewriting the laws of physics in their corner of the multiverse. What's exhilarating is that we're already part of this ascent. Breakthrough Starshot aims to send nanocraft to Alpha Centauri, a baby step toward interstellar engineering. Solar satellites and fusion research edge us toward Type 1. The scale isn't a prophecy, it's an invitation. every watt we harness, every star we study, writes another line in humanity's application to the universe's grand narrative. And if we're lucky or persistent, we might yet glimpse the next chapter being written by hands far older than our own. What if the Big Bang wasn't the beginning, just the latest chapter in an infinite saga of cosmic rebirth? Ancient Hindu texts describe the universe as breathing in and out, expanding and collapsing in cycles lasting trillions of years. Modern physics might be catching up to that vision. Roger Penrose's conformal cyclic cosmology paints a staggering picture. Black holes, those ultimate devourers of matter, could become the seeds of new universes. As they slowly evaporate via Hawking radiation, their energy doesn't just vanish, it gets stretched and reset by the expansion of space, eventually triggering a new Big Bang in a distant future where time and space lose all meaning. The equations suggest a haunting symmetry. The universe's fiery death could be another's birth, linked across eons by a hidden geometry only mathematics can see. Evidence might already lurk in the cosmic microwave background. Penrose and colleagues claim to have spotted faint, circular patterns in the CMB, imprints of supermassive black hole collisions from a previous cosmic cycle. These Hawking points glow slightly hotter than their surroundings, like cosmic tattoos left by a universe that came before. Skeptics argue these patterns could be statistical flukes, but if confirmed, they'd rewrite our origin story entirely. Imagine holding a fossil not from Earth's past, but from a reality predating time itself. The poetry of this idea is undeniable. Instead of a lonely, one-shot universe doomed to heat death, we're part of an endless loop where every ending births a new beginning. Black holes, often seen as tombs, become cosmic wombs. The laws of physics aren't arbitrary rules but self-perpetuating echoes, refined over countless cycles. Even the apparent fine-tuning of our universe, those precise constants allowing life to exist, could be the result of cosmic natural selection, with each iteration subtly tweaking the parameters. Yet the questions multiply. If information survives between cycles, could traces of past universes linger in quantum fluctuations? Could black holes encode not just the data of swallowed stars, but blueprints for realities yet to come? The math hints at possibilities stranger than fiction, where eternity isn't a straight line but a Möbius strip, twisting back on itself in ways we're only beginning to glimpse. Whether Penrose's vision holds or not, the allure remains. The universe might not have a single story, but an infinite shelf of sequels, each one waiting to unfold. Simulation hypothesis: are we characters in a cosmic code? If advanced civilizations run ancestor simulations, statistical odds suggest we're likely in one. Glitches in quantum behavior or mathematical constants might reveal the code. Is reality a layered narrative with deeper levels undiscovered? The hypothesis reframes existence itself. What if the universe isn't the base layer of reality, but a digital construct, a simulation running on some unfathomable supercomputer? Philosopher Nick Bostrom's famous argument goes like this: if civilizations inevitably reach the technological capacity to create hyper-realistic ancestor simulations, digital worlds indistinguishable from physical reality, then the number of simulated minds would vastly outnumber biological ones. Statistically, odds are we're in one of those simulations. It's a dizzying thought, but it's not pure speculation. Quantum mechanics already behaves like optimized code, with particles existing in superposition until observed, as if rendering only what's necessary to save processing power. Even the speed of light could be a built-in limit, preventing the system from overloading. Then there are the glitches, anomalies that hint at underlying code. Ever experienced déjà vu, that eerie sense you've lived a moment before? Some jokingly call it a rendering error. More seriously, physicists have found mathematical constants like the fine structure constant suspiciously precise, as if dialed in by hand. Others point to quantum entanglement, where particles instantly influence each other across vast distances, a feature that, in a simulation, might simply be data sharing between 2 points in the program. Even the pixelation of spacetime at the Planck scale, the smallest possible unit of space, could be evidence of a cosmic resolution limit. But here's the twist: if we are in a simulation, the creators might have layered simulations within simulations, like nesting dolls of reality. Each layer could have its own physics, its own rules, with beings inside unaware they're part of a grander experiment. The idea reframes everything from consciousness to free will. Are our choices our own, or lines of predetermined code? Is the universe's story pre-written, or are we, as simulated entities, capable of surprising our creators? The simulation hypothesis doesn't just challenge science, it blurs the line between technology and metaphysics. Some researchers propose experiments to test it, like hunting for computational artifacts in high-energy particle collisions or searching for repeating patterns in cosmic rays. Others argue that if the simulators didn't want us to know, they'd erase the evidence the moment we got close. Yet the most profound implication isn't about proving or disproving the theory, it's about what it means for our place in the cosmos. If reality is a construct, then every galaxy, every thought, every law of physics is part of an elaborate narrative. We might be characters in someone else's epic, but that doesn't make our journey any less meaningful. After all, even simulated stars shine. And if the universe is code, then curiosity, our drive to decode it, might be the most real thing of all. String theory proposes that the universe's tiniest building blocks aren't point-like particles but infinitesimal, vibrating strings, each oscillation producing a different note in the cosmic symphony. Picture a violin string, pluck it one way and you get an electron, another, and it becomes a quark. These strings are so small, about 100 billion times tinier than an atom, that they appear as particles to our instruments. But their vibrations might hold the key to unifying all forces: gravity, electromagnetism, and the nuclear forces, all emerging from the same fundamental strings dancing in higher dimensions. The catch: these strings don't just wiggle in the 3 dimensions we know. They vibrate in 6 or 7 extra dimensions, curled into shapes called Calabi-Yau manifolds, intricate, multidimensional geometries resembling crumpled paper at scales too tiny to perceive. Imagine blowing smoke rings. From a distance they look simple, but up close, their twists and knots reveal hidden complexity. Calabi-Yau shapes do the same for spacetime, determining how strings vibrate and thus what particles and physical laws emerge in our visible universe. Change the manifold's geometry, and you'd rewrite reality itself, tweaking gravity's strength or the mass of an electron. String theory's most tantalizing promise is M-theory, which stitches together 5 distinct string theories into a single framework by adding an 11th dimension. Think of it as the Rosetta Stone of physics, revealing that these theories were just different perspectives on a deeper structure. In this 11D reality, strings aren't the only players. There are also membranes, or brains, multidimensional surfaces where entire universes could exist like pages in a book. Collisions between brains might even trigger big bangs, suggesting our universe could be one of many, each with its own unique physics. Yet for all its elegance, string theory faces fierce criticism. It makes staggeringly few testable predictions, and the energy required to probe strings directly is a quadrillion times beyond our particle collider's reach. Some argue it's not science but metaphysics, a beautiful mathematical story with no experimental ending. Others counter that indirect evidence, like spacetime's quantum fuzziness or black hole entropy, already hints at strings reality. The debate isn't just about equations, it's about how we define truth in science. Is math enough, or must nature itself weigh in? Whether string theory is the universe's ultimate grammar or a dead end, it's reshaped how we see reality. It turns the cosmos into a musical score where particles are notes and dimensions are hidden harmonies. And if it's right, we're not just observers of this symphony, we're vibrations within it, fleeting chords in an eternal song. At the heart of every black hole lies a cosmic contradiction, a place where Einstein's general relativity, which paints gravity as the bending of spacetime, collides violently with quantum mechanics, where particles flicker in and out of existence like static on a cosmic radio. Relativity says matter crushed into a singularity warps spacetime infinitely. Quantum theory insists no particle can be pinned to a single point. The result? A mathematical screaming match, equations that explode into nonsense when pushed too far. It's as if the universe wrote two brilliant but incompatible drafts of reality and forgot to reconcile them. Enter loop quantum gravity, a radical rewrite that suggests spacetime isn't smooth and continuous, but woven from tiny, indivisible threads, like a fabric stitched together from finite loops. Picture a pixelated screen, but where each pixel is a Planck-scale knot of gravitational field. These loops twist and interconnect, creating the illusion of continuous space, much like a movie's frames trick the eye into seeing motion. In this model, black holes don't end in singularities but rebound in a quantum bounce, potentially birthing new universes. The Big Bang itself might have been the echo of a collapsed predecessor, a cosmic phoenix rising from its own ashes. Meanwhile, string theory takes a different approach, proposing that particles and even gravity itself are vibrations of microscopic strings dancing in hidden dimensions. Here, the clash between relativity and quantum mechanics could resolve in higher dimensional harmonies, where gravity isn't a force separate from the others but another note in the string's symphony. The catch: these extra dimensions are curled into shapes so tiny, they're effectively invisible, like ants navigating the folds of a crumpled handkerchief. The search for proof is where things get thrilling. Gamma-ray bursts, those fleeting but violent flashes from the distant universe, might carry fingerprints of spacetime's granularity. If space is truly pixelated, high-energy photons traveling across billions of light-years should arrive at slightly different times, like raindrops hitting a bumpy windshield. Telescopes like the Fermi Gamma-ray Space Telescope hunt for these delays, hoping to catch spacetime in its most raw, unfiltered form. Yet the implications go far beyond black holes or elusive particles. Solving quantum gravity could reveal the universe's foundational language, whether it's written in loops, strings, or something stranger still. It's the difference between reading a story and understanding the alphabet it's written in. And if we crack the code, we might finally answer the ultimate question: is the cosmos a single, elegant equation, or a patchwork of deeper, weirder truths waiting to be stitched together? The universe's greatest plot twist could be that its two biggest theories aren't rivals at all, just different chapters in a story we're only beginning to decode. The universe's constants aren't just numbers, they're lifelines. Imagine tweaking the cosmological constant, that mysterious energy stretching space apart, by just one part in 100 million billion. Suddenly, galaxies never form, stars flicker out before igniting, and the cosmos becomes a featureless void. Or adjust the strong nuclear force, the glue holding atoms together, by a hair's breadth, and protons either refuse to bond or cling so tightly no chemistry can unfold. The precision isn't just impressive, it's eerie, as if the universe's dials were set with life in mind. This is the puzzle of cosmic fine-tuning. Take carbon, the backbone of DNA and all organic molecules. For it to exist, stars must forge helium into beryllium, which then captures another helium nucleus in a rare three-step dance. The odds astronomically slim, unless the resonance levels of these atomic nuclei align perfectly, which they do. Physicist Fred Hoyle famously predicted this alignment before it was confirmed, stunned by how precisely nature's constants conspired to make life possible. It's like walking into a library where every book just happens to be written in your native language, except the library is the cosmos, and the language is the delicate balance of physics itself. So how do we explain this? One answer is the multiverse, a frothing sea of universes, each with random constants, where we simply inhabit the rare oasis where numbers aligned. It's the ultimate lottery, trillions of barren realities, and a handful where stars, planets, and thinkers emerge. String theory's landscape of possible universes lends weight to this, suggesting physical laws could vary across cosmic bubbles like dialects of a deeper, hidden language. But others see a different story. The fine-tuning argument, embraced by some theologians and philosophers, posits that such precision hints at intentionality, a cosmic architect setting the parameters for life. It's not proof, but a whisper of something beyond pure chance. Even atheist physicist Paul Davies concedes the universe seems suspiciously hospitable, as if it knew we were coming. Yet a third camp argues fine-tuning might be an illusion. Maybe life isn't the miracle we think, but an inevitable outcome of deeper, undiscovered physics, a universe where constants must take these values, locked in by some grander symmetry. Or perhaps consciousness adapts to whatever physics it finds, making any universe seem designed to its inhabitants. The debate straddles science and philosophy, probing not just how the universe works, but why it's this way at all. Whether through multiverses, metaphysics, or undiscovered laws, one thing's clear: the cosmos didn't have to be this hospitable. And yet, here we are reading its story, written in constants so precise, they feel like a message waiting to be decoded. The next era of cosmic discovery is already unfolding, not in distant galaxies, but in the labs and algorithms right here on Earth. The James Webb Space Telescope, with its golden honeycomb mirrors, has already peeled back the veil on the universe's toddler years, capturing galaxies so ancient they shouldn't exist. But this is just the opening act. The upcoming Laser Interferometer Space Antenna, LISA, will listen for the faintest whispers of gravitational waves, ripples from colliding black holes so massive their mergers warp spacetime itself. Imagine tuning into a cosmic symphony where every note is a cataclysm from billions of years ago, revealing how the universe's largest structures grew from primordial tremors. Meanwhile, artificial intelligence is becoming astronomy's newest collaborator. Machine learning algorithms sift through petabytes of telescope data, spotting patterns no human eye could catch. In Chile, the Vera Rubin Observatory will scan the entire southern sky every few nights, generating more data in a year than all previous astronomy combined. Without AI, we'd drown in the deluge, but with it, we might uncover subtle anomalies: a star that dims in unexpected ways, a galaxy rotating too fast, or even technosignatures hinting at intelligence beyond Earth. AI doesn't just process numbers, it learns the universe's habits, then flags the moments when reality breaks its own rules. But the story isn't just for professionals. Citizen science projects like Galaxy Zoo and Zooniverse invite anyone with an internet connection to classify galaxies, track asteroid paths, or hunt for exoplanets. A schoolteacher in Nairobi might spot a supernova. A retiree in Oslo could help map dark matter, This isn't just crowdsourcing, it's a collective awakening, a reminder that the cosmos belongs to everyone. The most thrilling chapters may lie in the gaps between disciplines. Quantum computers could simulate black hole interiors, testing theories about what happens beyond the event horizon. Neutrino observatories buried under Antarctic ice capture ghostly particles from supernova, revealing how stars die in real time. And as we stitch these threads together, we're not just observers anymore. We're translators, decoding a story written in gravity, light, and time, one that's still being written, with us as both audience and co-authors. As we close this cosmic odyssey, remember, the universe's patterns are more than data. They're a story written in starlight and spacetime, a narrative where every galaxy, every quantum flicker, is a sentence in a grand, unfolding epic. Think of the Fibonacci sequence echoing from sunflower seeds to spiral galaxies, or the way black holes punctuate the cosmos like dramatic ellipses, leaving us hanging on the edge of revelation. Even dark energy, that mysterious force stretching the universe apart, feels like a plot twist we're only beginning to decipher. Each discovery isn't just a fact, it's a stanza in a poem billions of years in the making, and we're the lucky readers turning the pages. But here's the real magic. This story isn't locked in some distant archive. It's alive, evolving, and you are part of it. The calcium in your bones was forged in a dying star's final blaze. The oxygen you breathe is a gift from ancient supernova. Even the electricity firing through your neurons right now, as you ponder these ideas, traces back to the same quantum rhythms that govern spinning electrons and swirling nebulae. You're not just observing the universe's tale, you're a character in it, a fleeting but vital sentence in its infinite script. So let's keep turning those pages together. Which cosmic mystery captivates you most? Is it the eerie synchronicity of fractal patterns, the haunting silence of the Fermi Paradox, or the way quantum particles seem to dance to an unseen tune? Drop your thoughts below, because curiosity is how the universe writes itself forward. And if you're hungry for more journeys into the unknown, hit subscribe. The next chapter is always being written, and with every telescope pointed skyward, every equation scribbled on a napkin, we're adding our own lines to the story. The cosmos isn't just out there, it's in you, in us, in the endless quest to understand, and that's the most beautiful pattern of all.